Hey guys, here we are in our unit about thermochemistry. This is the study of heat and heat flow. So a few things we'll talk about today. We'll just talk about how energy and heat are related. We'll classify some vocabulary, really, is what this unit's about. So here are a few questions that we'll be able to answer after we're finished with this unit. This is kind of what thermochemistry is about. So up here, say you have two objects that are in contact together. Will heat flow from the warmer object to the cooler, or from the cooler object to the warmer? Think about that. Say you have two metal blocks touching each other. One's at 100 degrees Celsius, one's at 50 degrees Celsius. Which way is the heat going to flow? What do you know about calories? We all know about food calories. So calories are a way to measure heat. We'll talk a little bit about the conservation of energy, just like the conservation of mass. Mass is not created or destroyed, and neither is energy. It all has to be accounted for someplace or another. Which would feel hotter, a puddle of water or a nearby iron sewer cover? Which would feel hotter? I think most of you realize that the iron sewer cover is going to feel hotter than the water. We'll find out why. Which would need more energy to heat up, the Verrazano Bridge or a box of nails? Obviously, the Verrazano Bridge is very large compared to a box of nails, so it's going to take a lot more energy to heat up an entire bridge than a box of nails. These are the things we'll be talking about. So first off, as I mentioned, thermochemistry is a study of heat changes that occur during chemical reactions. Most all chemical reactions either give off heat or they absorb heat, which would make things feel cooler. Think about a cool pack. When you break a cool pack and you put it on your arm, it feels cold because the cold pack is actually absorbing the heat from your skin, which makes it feel colder. So what is heat? Heat is thermal energy that transfers from one object to another because of temperature differences. So it's always this difference in temperature that we're able to measure in chemistry. One of the key concepts is it always flows from hot to cold. So in the example before, if you have a cold metal block and then you have a hot metal block, the hot metal block is going to transfer its heat to the cold side. Eventually an equilibrium will be achieved when both objects are going to have the same temperature. So it always goes from hot to cold. When we start doing calculations in the next section, heat is represented by the letter Q. So we'll get into that later. So what is energy? Thermal energy is what we're talking about in chemistry. Energy associated with the motion of atoms and molecules. So atoms and molecules are always in motion, or they're at least always vibrating. Even a piece of metal, the atoms aren't moving around inside that piece of metal, but say you put a piece of metal into a Bunsen burner and you start heating it up, what's going to happen is those atoms are going to start vibrating more quickly. And this is what we mean when we say thermal energy. Energy has no mass, and it's only detected by its effects. There's no mass or volume with energy. The law of conservation of energy states that in any chemical or physical process, energy is neither created or destroyed. It's always transferred from some place to another. It just doesn't disappear. Same as with matter. So when we're studying heat changes, we first must identify what the system is. The system is the part of the universe that you're studying. Whatever you're studying, that's the system. The surroundings are everything else around it. So here we have this guy sitting here by the fire, and if we're studying him, he's the system. The heat and the fire is the surroundings. So he's absorbing the heat from the surroundings, We have to make this distinction that if heat is flowing, we have to define what it's flowing from and to. So we call that the system and the surroundings. Two key vocabulary words here. We have exothermic and endothermic. First off, exothermic, it's the release of heat from the system to the surroundings. So say we're studying this bonfire here, it's releasing heat into the surroundings. It's exiting, exothermic, the heat is exiting the system. Humans, we're exothermic beings because we're always giving off heat. Our body temperatures are 98 degrees. If we exercise, we generate some more heat, so we're releasing heat. Here's a chemical equation. There's a typical combustion reaction. We have some kind of hydrocarbons with some oxygen, produces CO2 and water plus energy. The energy is over here, but the energy is over here. It's on the product side. So whenever you have a chemical reaction and you see the word energy on the product side, that means it's releasing energy. It's giving off energy. So that's an exothermic reaction. So here we have an endothermic process. Endothermic means absorbs heat from the surroundings to the system. So if your system is the ice cubes here, you're interested in the ice cubes, they're melting. The ice cubes are absorbing the heat from the surroundings and causing them to melt. Here's a chemical reaction. This is something you've probably done at home. You have some baking soda and some vinegar, and you put them together, it makes fizzy, it gets all bubbly. What you're actually doing is you're making sodium acetate, water, and carbon dioxide, or the bubbles that you're making. But notice energy, the word energy is on the left side of the arrow. These are your reactants. So when energy is a reactant, that means it's absorbing the heat, it's absorbing the energy. If you did this reaction, try it at home when you have nothing to do. Take some baking soda, put in a little bit of vinegar, and feel what that bag is like. Is it hot or is it cold? It's going to feel cold because the bag, this reaction, is absorbing the heat from your hand. If it's taking heat from your hand's going to start feeling cold. This is what an ice pack would do. So calories are a way to measure heat. 1 calorie is defined as the heat required to raise 1 gram of water by 1 degree Celsius. We typically use Celsius in thermochemistry. It's not like gas laws where we use Kelvin all the time. You could use Celsius. Food calories, these are food calories, a capital C. Really, capital C, lowercase c, these are two different things, so you got to be careful here. Big C calories really is a kilocalorie. 1 big C calorie is a kilocalorie, which is 1,000 little c calories. So when we're talking about food, we're really talking about kilocalories. If you have a food app on your phone and you track your calories, I do because it's really the only way it keeps me from gaining weight, the units will say kilocalories for the most part. And remember, when we're talking about this, it's big C calories, little c calories, two different things. A joule is another unit that we use to measure heat. You know how science is, there's always units for everything and different ones. So the calorie is related to the joule in this way. 1 joule is 0.2390 calories, or you could say 4.184 joules is 1 calorie. Either way, back and forth. It's just another way to measure heat. Here's another good vocabulary word for us, heat capacity. Heat capacity is defined as the amount of heat needed to increase the temperature of an entire object by 1 degree C. So this depends on how big the object is and what it's made out of. All right, so the very first slide we talked about bridges and boxes of nails. So which has more mass? Obviously a bridge is way bigger than a box of nails, so it's going to take a lot more energy to heat up an entire bridge by 1 degree C than you need to raise the temperature of a box of nails by 1 degree C. So if you had a question like which has a bigger heat capacity between these two things, you would say the bridge, because the bridge is simply bigger. It would take a lot more heat to heat this whole bridge up by 1 degree. Specific heat is kind of like the calorie, but everything has a specific heat. Aluminum, glass, mercury. So again, it's the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So this is what a calorie is. 1 calorie is you're raising 1 gram of water by 1 degree C. This is what it is in joules. Joules, calories, see how they compare. How about aluminum? Look at aluminum. Look how it's much less than water. Look how everything is much less than water. Water has a very high heat capacity. It actually takes a lot of energy to raise the temperature of water. It has to do mostly with the hydrogen bonds in water. You have to break those bonds, but we really won't get into that here. But think about it. If you heat up a piece of aluminum, it's going to heat up pretty quickly because, look, you don't need that much energy to heat up aluminum compared to something like water. You need a lot less energy. This is why aluminum is going to feel hotter than a bucket of water that's sitting right next to it in the sunshine. Glass is even lower. Glass heats up very quickly. Mercury has a very low specific heat and it heats up very fast. So here we are comparing a puddle out on the sunshine in the water or some metal bars. I think you would realize intuitively that the metal would feel hotter. Even the same temperature outside, say it's 80 degrees on a nice June day, the metal is going to seem hotter than the water. The water, it takes a lot of energy to heat water up.